Yeah,
Yes.
you can start
Okay.
your speech.
Okay. Yeah. I'm just starting now. Hello, everyone. My name is Zhao. I am working for the University of the Pennsylvania State in American. And so today I will give the presentation, and that is the comparative performance of analysis of the single-shot detector and the Faster RCNN for the object detector. So let's look about today's agenda. Let me just I think there's some sorry, and then let me just for screen, and then I can just okay, good. So let's look about the agenda. And so today I will introduce the image recognition and object detection, single-shot detector, and the faster RCNN. And I will use the COCO data sets and the annotation proposed the performance evaluation for the object detection. And I will also analysis about the experiment that both our professors conducted, and also were just explain some of the data analysis. Last one is the conclusion. And so let's start it. So we know that the right now, the computer vision with AI is a very hot spot. And so how can we apply the AI into the computer vision is us, like the scholars and the educators need to, or researchers need to consider. And so first of all, we need to know what is the concept of the computer vision. So computer vision is to understand a thing by creating a human-like vision. And so for the implementation, we can construct the neural networks like the convolutional neural network and the deep learning neural network for implementation. And also we need the extra CV computer visions libraries like the OpenCV and the PIL mentioned here. So what is PIL? So PIL is a Piro image libraries. And so those of the libraries are very important for the computer vision. And so for the application of the computer vision, there actually is a very wide range of the application. For example, like the self-driving cars, the Teslas, the self-driving cars very popular nowadays. And also we can think about the surveillance, like the robotics, they can just monitor the assembling lines, the productions. So we use the surveillance in the manufacturing industries. And also we can use the computer vision into the medical diagnosis. Okay, so now in order to apply the object detection, first of all, we need to know two different CV applications. First of all is we will think about try to implement the simple CV. So that is we call the image recognition. If you look about this, the slides here, so image recognition is to identify the main object, and that means it's only one front ground is the object, and from the background of the image. So you will see both of the picture in the slides. We can recognize the vehicle, the truck pickup from the picture left-hand side, and we can also recognize a groundsmith from the right-hand side of the image. But we need to know that there's only single class that we can recognize from this the recognition. And so unlike the image recognition, and right now we want to implement the more advanced, the more intelligent level of the computer vision, and that is object detection. And so by the concept, the object detection is to detect multi-classes objects by localizing their positions in an image. So that is called object detection. If we look about the image here, so in this image, there's several types of the fruits and the veg in the image. For example, there's orange, apples, broccoli, and the bananas. And so by object detection, we can detect multi-class of these fruits and veggies in the image. So we think about the object detection is advanced level of the intelligence for the computer vision. So that is we want to develop for this object detection. Now, the thing is that in order to apply the AI into the computer vision, there do have some of the challenging for the application and the implementation. So here in both of the slides, I would like to list all the challenges that we confront to develop the object detections for the CV application. So first, the challenge that we confront is from the object detections application. Basically, there's three aspects of the challenges. First of all, there's two of the challenges for this CV application. First of all, is challenging is to select the object detection models. We know that there's so many object detection model provision, like there is a single stage algorithms or there's a multi-stage algorithms. But those of the object detection models lack of the the guidelines, the use of the guidelines. For example, like what kind of the model is good for the small object detection, or what kind of the model is better for the real time object detection. So such kind of the guidelines is limited for us, even though we have a lot of the options or the provisions from the object detection model provision. The second challenge for the object detection application is that there's a limited the options for us and to use for the public large image data sets. So we know that in order to train the model like the object detection, we need a large image data sets. But actually, there's a limited as we can publicly use. So that means we need to, first of all, select we need to collect all of this, the image data sets, and then we were just think about how to implement, use this large image data set for the model training. So that is the second challenge that we confront for the object detection application. And next ones, I would like to talk about the challenging for the object detection implementation. Actually, there's three challenges. First of all, is that we know that in order to detect multi-object in an image, we need to, first of all, localize the object into somewhere else in the image as the bounding box. And then based on the bounding box, we can just recognize if the object is similar as the ground truth, the classification labels. So, but the thing is that how many objects in an image, actually it's a variance. So we cannot fix the object number in an image. So that add the challenging for our implementation of the object detection. Second challenge is that we also need to concern about the very area of the bounding box for the specific object in an image. Now, so say for instance, if we talk about the architecture in an image, that should be large and giant. But if we talk about there is small animals like the ant, that's very teeny tiny areas. So based on the different object, we should just use the variance area of the bounding box to detect the different object. And that is also the challenging for our implementation of the object detection. And the third challenge is for the annotation. And we know that once we create or we construct a model, train a model, the purpose for model training is we try to make the prediction to estimate how many objects in the image and what are they in the image. So the way we can implement the estimation is we will compare the prediction from the model with our ground truths. The ground truths most of the times are given. So for example, if we have an Apple image, so we will just give the label of the ground Smith, and then after the model training, we get annotation like the ground Smith, and so that we can just compare the prediction, which is ground Smith, with the ground truth of the ground Smith. And if they're the same classification annotation, and we think the prediction model is show us the good performance. So this is a way we should give annotation. However, in reality, if we try to use the large image data set, that means we cannot make annotation manually. And but if we think about another way for implementation, like the automation animation for the image label, image classification label, so far it's still limited for us to implement the automation image and annotation. So that is the third challenge for our object detections implementation. Now, based on the challenges that we faced on, we still want to evaluate the different algorithms for the object detection. So in this paper, I use two of the algorithms for the performance evaluation for the object detection. So the first algorithm that I use is a single-shot detector, and that is from the single stage algorithms. And the second type of the algorithm that I use in this paper is a Faster RCNN, that is from the multi-stage algorithms. So I will compare both of the algorithms from perspective of their structure, there's pros and cons, and their applications to make the comparison. So let's talk about the single-shot detector. Single-shot detector is combined with the object classification and the localization in a single procedure forward pass to the output. So this is called the single-shot detector. The SSD has a structure, and such a structure we think about is if it is in the neural network that is depth-wise separable. So that is we can implement the single-shot detector in real-time running model. So it is also the pros of advantage for the single-shot detector. However, the single-shot detector also have some cons. That is just lack of the fault tolerance. So that means if compared with the faster RCNN, SSD may provide the less recognition precisions. So this is the SSD's characteristics. Let's look about the faster RCNN. So the faster RCNN is combined with the object classification and the localization in several stages passes through to the model implementation. And the structure is the original, it's called the Regional Proposal Network, RPN, for the object localization. And the advantage for using the fast RCNN is its robustness for the recognition accuracy. And it also has some, the cons that is, it's compared with SSD, the fast RCNN runs a little bit slower than the SSD. So those are the difference and the differences between the two of the algorithms. So in order to evaluate the performance between two types of the model for the object detection, and we still need some of the merits or the standards. So here I use the merits from the large scale visual recognition challenging. And so there's two merits in specific. So first one is a running time efficiency. Is that quickly or is that slower for running the model? And the second merit is about the recognition accuracy. Is that, you know, the high or low precision for the recognition the model. So those are the two merits for the object detection. And so the data that I use for this paper is I use the COCO data, and COCO data is the large image set, and it's just a public image set. So the COCO data, it has the 91 object, or we can regard it as a 91 class categories. For example, like the person, vehicle, the animals, and the furnitures, something like that. And but based on the 91 categories, we in the COCO data also has the super categories. Basically, there's a 12 super categories like the furniture, appliance, sports, and something else. So according to the different times, the COCO data have the different versions. For example, there's a 2014 version COCO data, there's a 2015 version COCO data, and a 2017. So this is the COCO data that I use in my paper. So this is an example this is a sample pictures. I just select from the COCO data, and you will see there's each of the pictures, they're not just the single object, there's a multi-class in each of the pictures. And so that's why I choose COCO data as a good image data set for the object detection. So in order to measure the object detection model quantitatively, and so I gave the equations. It's called the intersection of the union. So this equation is help to get the different numbers of the bounding box through the model predictions. So let's look about the equation here. The intersection of the union is calculated from the area of intersection divided by the areas of the union. So how can we understand about the area intersection is here we compared it with, like I said before, we compared it with the model prediction and the ground truth, which is observation data. And so we compared the two of the area, both of the two things are area. And so if they have the overlapping, and we think about such overlapping area as the intersection, and also we need the area for the union. So the calculation of the area for union is a result from the ground truth area plus the prediction area minus the intersection area. So those of the equations are actually a derivative from the discrete math. And so this is the equations for the intersection of the union. Now the question is here, why do we need the intersection equation? It's because we want to, like I said, we try to handle the object detection, right? So we want to, for the object detection, only knowing the class annotation, like the label, is not enough. Like the ground truth apple from the prediction, and then compared with the label of the ground truth apple from the observation data is not enough. That means we also need to localize the apple as object in a specific image and to see if the apple is really treated from the model as a prediction is really the similar as the area where the observation data tells us. So bounding box is a very important indication for us to implement the object detection. Now here is that is why we wanted to use the IOU equations here. However, if we look about the IOU equations, we know that in order to implement the IOU equation is complicated and also is time consuming. And that's why we think about if there's any of the the constant, you know, or the experimental, what I want to say is empirical, the constant that we could use, which is handy for our experiment. So that's why I look up several of the references papers showing here. So you will see that in the paper 26, they use a threshold of the IOU are 0.26 and 0.27, 0.49, 0.59, 0.65. And in the paper of the 27, in the paper, and they said that the constant threshold is the 0 and 0.125. And in the paper 28, the constant threshold are the 0.38, 0.56, 0.67, and 0.76. Now, compare with this variant range of the constant IOU threshold, we need to figure out what is the real, what is the good, the empirical data as a constant IOU threshold that we can use for the object detection. So that's why I just I conducted the experiment and try to estimate which the constant IOU threshold is really good one for the object detection. But before I explain about my experimental implementation, I would like to introduce the other four the case studies for explaining the TP, FP, FN, and TN. So the TP, FP, FN, and TN are actually the concept that is very popular used for the statistics models, but we can use it here for our performance evaluation of the object detection. So I use the pictures, which is from COCO 2017's validation data set. And the picture is 0000885.jpg picture. But before we look about the picture, let's look about the definition or the explanation for TP, FP, FN, and TN. So what is a TP? So TP is a set bounding box makes the overlapping area greater than the prediction, greater than the IOU threshold. And that's the prediction class label is also the same as a COCO data annotation. So that is the definition of the TP. FP is a set bounding box make the overlapping area which is not greater than but less than the IOU threshold. Now here the IOU threshold is we can regard it as the constant IOU threshold. And so even though the predictive class label is the same as the COCO annotation, so that is a FP. And FN is a set bounding box in prediction is independent of the bounding box in the ground truth, no matter the class labels between the prediction and the COCO annotation. And the TN case is the set bounding box makes the overlapping area greater than the IOU threshold, but the predictive class label different from the COCO annotation. So this is the TN. Now, if we use this explanation of the case study of the TPFP, FN, and TN into the image, how it looks like. So we know that in this image that we used from COCO 2017, there's two color of the boxes. The green color represent the COCO annotation, and the red boxes represent the training model prediction. And so let's look about the top left pictures. And so this case is actually the TP's case, meaning meaning that the predictions threshold is greater than the prediction thread IOU thread is greater than the IOU threshold, and also both of the boxes have the same classification, the label. And so this is a TP case. And let's look about the top right. Top right case is the FP. So FP means that So that means that the IOU area after calculation, which is a red box, is less than the IOU threshold. We can regard IOU threshold is from the empirical data. So that's why we think, even though here maybe the annotation is the same, the person and person, but we still regard this case as the FP case. Let's look about the bottom left. So this case is we regard as the FN. So that means regardless the COCO annotation and the prediction label, and both of the box after calculation, the IOU is 0. So that means both of the box is independent with each other. So this is the case for the FN. And let's look about the TN case. So TN case is at the bottom right. So in this picture, we will see that both of the box overlap. Most of the areas overlap each other. However, if we look about their class labels, and the green box class label is person, and the red box the class label is sheep. And so we know that they're not the same class. And so this is a case for the TN. And so the case study here is try to help us to better explain and analyze the experimental result that I conducted in the following slides. And so let's look about the slides. Now, this is a slide for the pseudocode of implementing the single-shot detector and the calculation of the recognition accuracy. For the mean accuracy prediction is use the equations at the bottom. And so this is for the pseudocode of the single-shot detector. Based on the single-shot detector, I modify the code and implement the Faster RCNN. So for the modification part, I listed here, there's just the two parts. So for the time limit, and I just leave the time for you to read it after. And so let's look about the experiment here. So in this table, I compared two of the algorithms. One is a single-shot detector. The other is a Faster RCNN. However, most important thing is that I use the IOU threshold. The value is 0.25. So if I use the IOU threshold value is 0.25, it will just give me it will help me to get the different bounding box number for the prediction models. So that will affect the prediction accuracy. So this is the things that we need to know. So after experiment, and let's look about each of the columns in this table. So first column is I select the 8 high frequency of the class category object and listed here, which are the person, car, horse, tennis racket, cap, pizza, dining table, and laptop. And second column is just the bounding box number for the COCO data. And so this is the ground truth table. Sorry, this is the ground truth data. And the third column is I use the single-shot detector for running the COCO data to get the object detection, the running time, and the unit is a second. And the first column is a bounding box for prediction by using SSN. Let's skip the column 5 and just look about the column 6. And so for the column 6 is a running time for the Faster RCNN. And then for the column 7 is the prediction bounding box for each of the classes. And so the column 7 is for the recognition accuracy, which is percentage. Now let's look about the red colors for some of the rows. What does that mean? Now here is the thing. In order to get the recognition accuracy, the equation that I use is the bounding box number of the bounding box in the prediction divided by the number of the bounding box in the ground truth. And so that we know from perspective of statistics and the probability, so we know that the bounding box for prediction should be no greater than the bounding box of total bounding box of the ground truth, right? But here, if we set up the IOU threshold is too low, for example, the 0.25, it will create the situation like the bounding box in prediction is larger than the bounding box in the ground truth. And that should not be the case in reality. That's why we think about if the bounding box in prediction greater than the bounding box in ground truth, that lose the meaning to calculate the accuracy. That's why I just gave just a clause here. So that means that it's not an option for us. So this is for us to understand how to set up the low level or the low value of the IOU threshold. So instead, in the upside, I try to lift the value of the IOU threshold. So in this table, I increase the value of the IOU threshold from 0.25 to the 0.9. And now you will see all the red cross situations disappeared. So that means our threshold of IOU threshold constant value is high enough. However, such kind of the high value of the IOU constant threshold costs another thing. The issue is that if we compare it with the column 5, which is the accuracy, recognition accuracy for the SSD, and for person is 69.31, and car is 34, and house is 41, 12 for tennis racket, and then cup is 23, 25, 17, 16, and we compared with now the IOU threshold. If we set as 0.25, and we will find the tennis racket is greater than the 25, the 12 in the IOU threshold 0.9, and the same thing for the other the categories class. And so this is give us another the ideas that if we set up the IOU threshold constant is too high, and then we will narrow down our recognition accuracy. So you see, this is very tricky thing. We don't want to get the wrong cases for the estimation or prediction, but we still wanted to, guarantee the performance robustness, right? So that is a very tricky thing for us to choose the IOU threshold constant. So that's why I also get another 2 pairs of the IOU threshold constant in the paper, which is I choose the other the IOU threshold like 0.5 and also 0.75, and list the other two paper tables for the explanation. And so for the conclusion by this paper, the conclusion is listed here. So the first one is that the advantage that I use the constant IOU threshold is simplifying the computation in the implementing both of the algorithm for the object detection. And the second conclusion is here, the selection of the constant, the threshold is very tricky for the object detection performance, because the IOU threshold determines performance robustness and the recognition accuracy. So in the first place, the small value of the IOU threshold, which fields in more predictive cases, will trigger the unstabilized performance evaluation because the predictive cases may include both TP and FP cases. In the second place, the larger IOU threshold or high value of the IOU threshold will ensure the stability in performance evaluation. However, it will narrow down the possibility of the recognition accuracy because IOU threshold is inversely proportional to the recognition accuracy. So let's look about the conclusion. Third one is that for object detection using COCO data 2017 validation, SSD is proved to be more optimized.